Okay, well, thank you very much, everyone, for tuning in, and welcome to this first talk, which is part of the ALMA Recounts of Cosmic Conundrums series, organised by the European Art Network. The European Art Network consists of 7 nodes distributed throughout Europe, coordinated by ESO, with their main goal being to maximise ALMA's scientific return for European users. This includes providing virtual or real-life user support to anyone who wants to use or get to know more about ALMA, who needs support with data calibration and analysis, proposal preparation, archival science, and much more. But it also includes the organisation of talks like today's to celebrate and promote ALMA science in Europe, to stimulate interactions, and to build new connections. In every talk of the ALMA Recounts of Cosmic Conundrums series, a major astronomical question is discussed. The speaker describes the context of the question and then focuses on the ALMA contribution to the field, past and future. The aim of the series is to highlight the unparalleled contribution of ALMA to the broader astronomical landscape and to provide an outlook towards the future. Today, we are delighted to have with us Leen Decin, who will talk about flecks of extraterrestrial dust all over the roof, the story of their cosmic makeup. Leen is a full professor in stellar and exoplanet astrophysics at the University of Astronomy at KU Leuven in Belgium, where she has been based for most of the last 25 years, with a short period at the University of Amsterdam. And she also has a visiting professorship at the University of Leeds in the UK. I have known Leen for almost as long as ALMA has been operational, since she has led or participated in many projects studying mass loss from evolved stars in a very holistic way, looking at the interplay between stellar properties, chemistry, and hydrodynamics, and many other projects and many other ways of contributing to ALMA. As well as interpreting observation results, Leen is expert in modelling and the use of high-performance computing, applied not only to evolved stars, but to exoplanets, planet-forming disks, and many aspects of astrochemistry. Since 2004, Leen has been awarded the Frans van Cauwelaert Prize and the biennial Henri van der Linden Prize for Astrophysics and Geophysics from the Royal Flemish Academy of Belgium for Science and the Arts, and the prize of the Research Council of KU Leuven for Best Postdoctoral Researcher in Exact Science. And in 2016, she was nominated for the Jaarprijs Wetenschapscommunicatie, again, the Royal Flemish Academy of Belgium. And I do apologise for my terrible pronunciation of Flemish. I have to say, reading some of Leen's code, which is commented in Flemish, is also very difficult. I have learned a huge amount, as well as a minuscule amount of Flemish, but a huge amount of astrophysics from working with Leen and other members of the great group that she has built at KU Leuven and her network of collaborators. So I now hand the floor over to Leen.
Thanks a lot, Anita. Thanks a lot for this very nice and enlightening introduction of myself. I'm happy that you have invited me to give this first talk in this series of ALMA Recounts of Cosmic Conundrums. And I will try my best to fulfill your hopes and try to explain you some of the things that we have been learning throughout the years. I will now start with first sharing my screen. Anita, can you then, oh, not yet. No, it's the wrong one. So Anita, can you? I cannot see you anymore, but can you?
I can see your title slide.
Okay, fine. So then we start with the lecture of today. And so, as has been asked to me by the people from the ALMA nodes, is trying to explain you what we have learned upon dust enrichments and dust formation around evolved stars and what ALMA has contributed to that. And as you could see already in the abstract of my talk, I will try to explain you these things by not only linking to what ALMA has been showing us, but also by linking that towards the only and few things of extraterrestrial species that we have found here on Earth. And these are these very little, often very little micrometeorites that do tell us something upon the cosmic makeup, upon their formation, upon their history, and really are these very key diagnostics together then with ALMA observations that can help us in unraveling and in understanding how does this formation work in this quite hostile universe. And as such, you will see that I will start with these little stories upon what do we know about it? What do we know? Anita, can you see my mouse or not? Can I please ask you that first? Anita?
Yes, I can see it clearly.
Okay, thanks. So I will start telling you a little bit of the background. What do we know about these evolved stars? What do we know about what kind of dust species we can see there? But then also, what are then the constraints we get from this little meteorites? And often then the story is not only one way, but it's a combined way. And what do we know here from things we know on Earth, from these meteorites, from the lab? And how do we then translate that to universal knowledge upon chemistry, upon dust formation, that can happen throughout the universe? And so I'll start with that cover story that was published in New York Times in 2017, and where the person you can see here, on John Larson, so that's the person you can see here in the picture, started to wonder, if it's indeed true that roughly some 4,000 tons of matters, of extraterrestrial matter arrives on Earth every day. Where can we find it then? Since often we just don't realize that. And it's for sure, if these meteorites are very, very tiny, it's very difficult to find them. And he started that little project to start it and just look around at the roofs. And after some training of his eye, and in particular, after looking, towards what are then the specific morphologies I do have, he started to get a feeling upon which of these little dust species I can find on a roof, which ones are potentially of extraterrestrial origin. And then you cannot only do that from just looking towards the morphology, but what is the decisive making body is then looking to the chemical makeup of this species. And so what do they tell us upon dust formation around evolved stars? So in order to tell you that, I will first start with giving you a short introduction into the topic of these evolved stars. Then I will explain you how telescopes can be used as microscopes. And then I engaged into the topic of corundum, given the name of this lecture series as being the conundrums. I hope I will not lose or miss during my talk, but we try to solve what is the conundrum of the formation of corundum. And then we will arrive back on planet Earth. So what is the focus of today's discussion, as has been asked to me by the organizers of this lecture series? We will focus on evolved stars. These are the stars that either if we have sun-like stars or either if we have stars more massive than 8 solar masses, they do transit into red giants and red supergiant stars, so the asymptotic giant branch stars and the red supergiant branch stars, before they either evolve towards a planetary nebula and then end the life as a white dwarf, or become a supernova and then end the life as a neutron star or black hole. So this AGBs and red supergiant stars, they are the key focus of today's talks. Why? Well, they're the focus since it is in these environments that we have already very good diagnostics and quite well understanding, I should say, upon how dust can be formed. And then we can translate that knowledge into all kinds of other astrophysical environments. Since these evolved stars, and you can see here the stellar evolution life cycle again, these AGB stars and these red supergiant stars, they develop a stellar wind. Right? For this type of stars, they are thought to be mainly for these AGB stars dust-driven stellar winds. And it is through these stellar winds and through then the mass loss that new particles are injected in the interstellar medium, and hence they arrive at other places in the universe, such as our own planets. And so if we are now talking upon what can be the composition of these stellar winds, this is for sure linked towards the composition of the host stars. And we know from the fact that these host stars, these evolved stars, are really kind of nuclear burning plants. We know that elements such as water and oxygen, carbon, silicon, nitrogen, etc., they are formed in these AGB stars, and through the stellar winds, these atomic species are injected into the interstellar medium. If you are now looking towards a composition of these stellar winds, today, roughly more than 100 molecules have been detected in stellar winds and more than 15 dust species. And as such, these stellar winds are really very rich, unique chemical laboratories. Coupling that towards what we know on the table of Mendeleev, you can see here in the different colors what is a contribution from different stellar origins and also from the Big Bang. And you can see here that is dying low mass stars, exploding massive stars, and exploding white dwarfs, that they are the main contributors towards the creation of the majority of the elements that we do see here in the table of Mendeleev. So now back towards the start of our story, these little micrometeorites and their origin. So if you are now looking towards these micrometeorites, you might wonder then, okay, how can I then know where they have been created? How can I know their birthplace? Since indeed, little dust species, they can form around these evolved low mass stars, but also massive stars. And also around supernova, we do see dust present. So how do I know it then? What might be the birthplace? Well, a very diagnostic way of tracing the birthplaces of micrometeorites is looking to their isotopic composition. And here you can see a picture from Roderis 2016, where you see the oxygen isotopic compositions on the X and Y axis. And depending then on the ratio that you have, you can see that some of them, for instance, this group 2 micrometeorites, or meteorites in general, they have an origin which is linked to an HEB star. While, for instance, the group 4 ones, they are thought to have been created in a supernova explosion. So this is something you have to keep in mind when I will now start trying to explain you what we have learned upon that particular way of dust formation. How can we get the formation of dust in these quite hostile environments? For sure, one of the main things we are using here is these telescopes. How can we use this new advent of telescopes, amongst which ALMA, to understand dust formation? So first of all, let's give you a little bit of a background on stellar wind physics, stellar wind chemistry and dynamics. So what you can see here in this graph is just a representation of a stellar wind. So the star itself is shown here as a first yellow half circle. And then you see different, roughly, regions in the extended atmosphere or in the stellar wind. And so in the first region of what you should know is that these HEB stars, they are pulsating. And as such, you get shocks in the environment. And these shocks will create a non-equilibrium gas phase chemistry. And then slightly further on out, where it's cooler, you can see the temperatures here shown at the top. It is cooler. And so there slightly further out, it is cool enough and still densities is high enough for these molecules to form larger gas phase clusters and finally condense into dust species. And then it's interaction with the photons that can give you enough photon pressure or radiative pressure for the wind to be accelerated. In the more outermost regions, photodissociation is happening. This is caused by the UV photons from the interstellar medium. They go through the dissociation, and you can see a very rich gas phase and gas dust chemistry taking place. So aiming to understand what is the chemistry here, but also, and for sure, aiming to understand how does chemistry drive the dynamics, and also vice versa. What is the impact of hydrodynamics on the chemical composition? We need to study the molecular composition, the dust composition. We want to understand how molecules form dust, and also how do grains and molecules react. ALMA for sure is a very great instrument trying to tackle each of these topics. I hope you, for instance, have seen this kind of a great images of great data sets of ALMA. This is one of PEPE CHANICARO, published in 2013 of ERC 10 to 16. This is one of the most well-known AGB stars. And what should take your attention is, first of all, that we can pinpoint the molecular features quite well of a lot of these species. So, and you see a very rich gas phase chemistry. You see sodium cyanide, you have SiS, you have calcium chloride, etc. But the other thing you should see is that there are still many unidentified features. And this is one of the great things of ALMA. We have this great spatial and great spectral resolution, that what was previously a kind of a very, that was kind of a continuum with some bit of a noise on it. Suddenly this noise is not anymore noise, but we see very distinct spectral features. So now it is upon us, the astrochemists, trying to understand what are these unidentified species and what can they learn us upon the molecular composition of these winds. So in my review paper of annual reviews of AMA, I have made a condensed table where you can see all species that have been identified so far in stellar winds. These are 105 species that have been identified in these stellar winds, but these are not the only molecules in the stellar winds. What I mean with that sentence is that, for instance, there are molecules of which we know they are there, but we cannot detect them. So there is still a difference between being and seeing. For instance, H2, which is the most dominant molecule in the stellar winds, is very difficult to detect since it's a non-polar molecule. And as such, we know it is there, and there has been a very vague detection potentially in some of the infrared molecular lines, but it is just, if you would use ALMA to detect H2, it's a no-go. You cannot have it since it doesn't have an electric dipole moment. The second thing that you should realize from this table is that out of these 105 molecules, 78 of them do contain carbon. And this has two reasons. For sure, carbon is a very reactive atomic species, and that is why you can have a that is why you can have many carbon-rich species that are formed. But on the other hand, there is also an observational bias here, since this AGB star that is the closest to us and with a high mass loss rate, so you need both so that you have a better chance to detect the species, is a carbon-rich target. It is the one that I have shown you in the previous slide. So it is this ERC 10 to 16. And as such, we have many molecules which have been solely detected in that star. Just for comparison, if I would look to an oxygen-rich AGB star, the closest one is closer to us. So it's a 150 parsec versus 60 parsec, roughly comparison. But its mass loss rate is roughly 2 or 3 orders of magnitudes lower. So it's much more difficult to detect the molecular species over there. So what do we also know from this kind of AGB stars? Well, we come towards the dust and the question on the dust formation. The challenge with dust, and this is here a spectrum from the Infrared Space Observatory, is that it is much more difficult to have an unequivocal identification of a dust species. And the reason from that stems from the fact that this dust spectral features often originates in radiatively excited functional groups of atoms constituting the grains. For instance, you can have this SIO stretching bands, and so such an SIO stretching bands can then give you these very broad bands around 8 to 10, 12 micrometer. But you know, SIO is a composition of various kind of silicates. And so it's not only SIO that potentially vibrate over there. There might be, for instance, also aluminium oxides that vibrate in the same wavelength region. So say, you know, if you have a very broad feature, being sure that you have, for instance, either silicates or aluminium oxides, it's much more difficult than saying, I have identified this or any other molecule. So how many of which dust species have been detected so far? We have roughly 16 of them that have been identified. Again, here I refer to that review paper. Also remark that the ones that I list here at the bottom, they are dust species which have been solely identified in meteorites, but not yet directly in the infrared observations, for instance, of evolved stars. I know they are there, but we could not yet identify them really for sure. There have been some tentative identifications, but they remain in the field of being tentative. So given now here this condensates that we have, you see that quite a few are linked to oxygen-rich chemistry, so Al2O3, alumina, you have the silicates, and then you have also iron, potentially water ice, and you have formation of carbon-based dust species. Today, I will mainly try to explain you the conundrum of corundum, and corundum is the crystalline format of alumina. So just remember that unit formula here, since that will give you a clue or an understanding of the rest of my talk. But let's first start with the carbon-rich environments. What do we know upon dust formation in carbon-rich environments? So one of the proposed pathways towards the formation of amorphous carbon is that we start with an acetylene chemistry, which then leads towards the formation of benzene and small PAHs, and then which then subsequently can build up to form then these larger amorphous carbon grains. PAHs have been identified already in meteoritic studies, so we know they are there. They're not always easy to detect in AGB stars, but there has been an identification in AGB stars where we have a carbon over oxygen ratio around 1. However, now I now go away from the carbon-rich stars, and we will focus on what is happening around oxygen-rich stars. So they have an oxygen over carbon-rich ratio above 1. And so gearing that discussion towards this oxygen-rich environments, how do we dare think that dust can form? Well, there are two pathways, they're presented together, that are thought that can happen. And so the proposition that you can see here is based on thermodynamic equilibrium reasoning. So if you have a thermodynamic condensation sequence, then you have two branches. The first branch that can occur is linked towards the aluminium oxides. And this is our question of today, we start with, at the highest temperatures, these sequences predict alumina to form. And then when we go towards lower temperatures, you see gillenite, diopside, anorthite, etc. If we look towards the silicate condensation, the thermodynamic condensation sequence, you see that I have shifted it. It starts at lower temperatures with the formation of forsterite. So forsterite is a silicate which does not have iron in its composition. Remind that, I will come back to that later on. It's purely magnesium rich. You have enstatite and you have olivine then with the potential also of having some iron in it. And so if you are wondering how does this form and what might be the first dust seeds, then given this proposition on thermodynamic equilibrium considerations, you would say, okay, the first dust species that can form close to a star, these are these alumina condensates. Is this true or not? So let's continue. So what do you need to understand? First of all, if dust grains are formed, I have told you that they are very important for a stellar wind to start, for a stellar wind to launch. So how does the mechanism work? If dust grains are formed, they can interact with the photons. So you can have photon absorption. You can have, again, after some absorption, you can have back emission, you can have scattering, etc. So throughout that process, there is a radiation pressure. You can show that there is a gain in the momentum of your particle, and so as such, your grain does gain some momentum from the interaction with the photons, and it is driven outwards, and then it collides with the gaseous species around, and gas is much more abundant than the dust species, and throughout its collisions, it shares parts of its momentum, and so also the gas species are driven outwards. So that this is the general physical mechanism of how it is thought that a stellar wind is launched. Okay? So now if this is the mechanism, and if you realize, so the previous slide, how these silicates and aluminum oxides are forming, you now understand how a wind is launched, then you have to think, okay, does it work? Well, we were quite happy with the story on these thermodynamic sequences, since it seems to work quite fine. Also when we were working on this infrared space observatory data, we could explain quite a lot of data from that consideration of thermodynamic equilibrium. And for people who are not used to think upon that, that's a very convenient way of explaining chemistry, since what you only need to do that kind of a predictions based on thermodynamic equilibrium is you need the pressure and the temperature of your environments, and then you know which species can form there. So in a way, you are not concerned upon the pathways, how your dust species is formed. You will get your dust species formed. You can just compare it with if you would have a little hill and a ball, and the ball rolls down the hill. As long as the hill is quite smooth, your ball will end up in the valley independent of the path that is taken. Well, that's the same with thermodynamic equilibrium. You go down the hill, you arrive at the valley, and there you have the dust species that I just have shown to you. Yeah? So it's very simple. Well, it's simplifying, since I don't need to understand all these chemical pathways in between. It just will happen. Well, we did use that framework, but then in 2006 there was this quite striking disruption of that quite comfortable feeling of, yes, we understand how it works. And then Peter Woutke published this paper. And so what you can see here, just follow my mouse, is that you see the opacity of these various dust species in function of the wavelength. So you see here these aluminium oxides, you see these magnesium silicates, so the ones which we think do form first. However, I explained you, we need the interaction with your star. So where do AGB stars emit most of their photons? It is in this wavelength region now indicated here in this yellowish color. But if you fold these two things, so the opacities with the behavior of your star, then you have a problem. Since where you see a huge crosslink between a lot of photons, you see that the species that form or that have a large opacity over there, they are iron-rich. But this implies that if they are iron-rich and have a high opacity there, they are very hot. It's even like that they are too hot to form close to a star. So these species, as a dust, cannot form since they would sublimate. We are only left with these other ones over there now in the white part of my diagram. But these ones do not interact very well with here this yellowish color of the star. So while these ones are too hot, The other ones cannot drive a stellar wind. So how to solve that dilemma? Various ways have been proposed to solve that dilemma. Either you're too hot or you cannot drive. And so one of the propositions was made by Suzanne Höfner in 2008. And she proposed that, okay, we can have these grains which have that very low opacity, so these ones, but maybe they can still drive a wind if they are large. So how does it work? Well, if grains get larger, instead of Rayleigh scattering to be dominant, you have the me-scattering, which starts to be more dominant. And the larger the grain, the larger the forward push is in terms of momentum transfer. And so you can see that if grains would be able to grow in size, and in particular, if they would have sizes around 200 to 300 nanometer, there is still that potential that they can drive a wind, although their opacity might be low in the near infrareds. That proposition has been confirmed or partly confirmed a few years later, when Norris et al. In 2012 published in Nature a paper using VLT-NACO observations, where they have shown that their data was not compliant with Rayleigh scattering, so small particles, but with me-scattering for grains which have a size around 300 nanometers. However, this kind of data cannot tell you what is the composition of the grains. And this is exactly the question that we aim to answer today. So can we form those grains that are large, and how can we understand that from a chemical point of view? So how to understand the formation from molecules to grains? How can we see how each of that is happening? And so the question we try to answer is, how can we go from molecules to clusters? We call that nucleation, and then from clusters to larger dust grains, which are then what we then call condensations. And so the scheme that is followed here is, a cluster is just an addition of several molecular building blocks of the same entity. For instance, you can have titanium dioxide, which is then growing in size, and as such, you can get larger and larger dust grains. So, and well, wait. I'm just confused now, since I think my computer skipped a few slides, but give me a moment. I will just check something very rapidly. No, it's fine. Sorry, I just continue now. So I'm here. You have these larger entities, and at some point, these larger clusters, they will condense and form a dust grain. Where that transition is not well known. But what you do need to see here is that in its format, in its structural geometry, there is a large difference between a small cluster, which is can be very irregular, and a larger species which starts to be a dust species, which is often much more regular. So how can these clusters form? There are two pathways, either a heterogeneous or a homogeneous one. A heterogeneous pathway is that you first have a little dust grain that is formed, little seeds, and then on top of that, other molecules can react. So which ones are thought to be the best candidates for that first seed? So the gray box here. Well, these are the ones you can see here. Given what we know upon AGB stars, upon oxygen-rich AGB stars, and then you need to take into account their abundance, their bond energy, how well do they react at high temperature, or do they dissociate, etc. These are the best candidates. However, throughout, let's say, the past 20 years, or even 30 years, quite a lot were thrown out of the picture. And the reason for that is either they didn't have a stable cluster, the nucleation rate was too low, etc. And then given them some new lab experiments, some of them, for instance, SIO came back into the picture, since there were new experiments, and then later on people were saying, no, I'll come back also to that one. If we really do chemical kinetics, it cannot be SiO. The best candidates until now are based on this titanium oxide or titanium dioxide. However, titanium oxides have a quite low abundance in AGB stars, so there is still a question mark there if these are indeed the best condensates for the first dust seeds to be formed. Another pathway is then homogeneous condensation. And so what you then have, for instance, is that one entity can form, for instance, the precursor of instatides, and then that can be the building block. And very nice DFT, so density functional theory calculations, have been done by Gomez in 2012, 2013, trying to understand if that could be, so you would have a direct gateway towards these instatides. And that can potentially work, but only it seems to be valid where you have high pressures. And so that would only be a potential explanation for stars with a high mass loss rate. So not for stars which do have a low mass loss rate. The main bottleneck here is the formation of the dimer of SiO, which is not very likely to happen. So actually, the only thing I can say, we don't know. So how then to solve that puzzle of dust formation in AGB stars or dust formation in general? So it's a combined crossroad. It's a crossroad of observations, of lab work, of simulations and theoretical computations. And I'm happy to propose here one of the contributions towards answering that question. And you will see that I will address most of the 4 Flecks ships I do see here, and also one of these ones which are linked to the Atomium large program, so one of the ALMA large programs that have started around 2017, 2018, and to which Anita has alluded already, where we are collaborating with some 45 colleagues from all over the world in order to understand that question and many other questions as well. So corundum the conundrum, how can we solve that, and what is then the contribution of ALMA? So we use a lot of instruments in order to unravel this stellar winds, since each of these instruments is sensitive towards a particular region of the stellar wind, as you can show here. And so first of all, what I want to highlight here already is the crucial role that Herschel has played us. I do show here one of my very old papers of 2010, and there it took us some 40 hours to observe 12 molecular lines of the most abundant species the second most abundant species in this stellar wind, so carbon monoxide. And then a few months later, Herschel came online, and this is a little movie, I will not show it now, but you can, it starts meanwhile. But so what you see here is that in a fraction of a few hours, more than 930 molecular lines have been detected in one of these oxygen-rich red supergiants. And so you can see here the movie which crawls towards the observations, and you see all of these identifications, which is wonderful. And it gives us a huge amount of information on the chemical composition. However, what you also can see here in this little movie is that the spectral lines are not resolved. And this, or barely resolved, most often not resolved. So that's a part of the puzzle that we are missing by using the Herschel kind of data. And this is the kind of information that we get thanks to that wonderful instrument that ALMA is. So while Herschel was so good in detecting a lot of lines, ALMA has not only given us the potential to detect these lines, but ALMA also gives us the potential to also locate where these molecular lines are excited. And on top of that, we have this high spectral resolution mode of ALMA. And so you can see here a movie of 2 oxygen-rich AGB star, Ika Tau and Erdor. So the red one is Erdor, Ika Tau at the bottom, with their line and identifications with these nicely spectrally resolved lines. And on top of that, okay, that's a mismatch now, but that's fine. We can now we know where each of these spectral lines is excited, close to the star, further out of the star. We can use that as a huge information of dynamics and of physics. Understanding that gas is of utmost importance if we also want to understand the dust that is formed there. So I will now remain my discussion, or I will focus the discussion towards Erdor. So it is the one that targets that has a very low mass loss rate, around 10 to the minus 7, but it's extremely close by, well, for me, extremely, around 60 parsec. And you can see its infrared spectrum here, where you can see here the potential identification of our question of today. Alpha, Al2O3, this is the crystalline form of Al2O3, and so this is what we call corundum. So ISO told us the dust is there, corundum is there. And also the infrared of the interferometric observations did show us that dust is formed very close to the star. And so what I indicate now with the white circle is the stellar surface. And you can see here the pattern of the dust here in this Collifer scale. So we see around where this red, that there is a lot of scattering of dust grains. And the analysis of this data did also show that these dust grains are large, around 300 nanometers. They are formed in a very hot environment, around 1500, 1800 Kelvin. But we cannot say what is the composition by using this data. There is still the preference towards corundum or aluminium oxides in general, since I just have shown you that they are formed at higher temperatures than the iron-free silicates. And then we got these ALMA observations of that target, of Erdor. And we did see, much to our surprise, that aluminium oxide is present close to the star, and it is even present in the region beyond where we can see that the dust is formed. Sorry, oh, that one goes too fast. So if you see here, oh, there is a miss, yeah, okay. So this is, if I would outline here where the dust is formed, so let's say roughly the outer region, this is compliant here with this white circle over here. So if these are potentially aluminium oxide grains, can we then still have aluminium oxides, which are the building blocks of that aluminium oxide grains? So if the grains are there, or vice versa, if I can see the gaseous species there, maybe this is immediately the answer, that this cannot be aluminium oxides. But before making this very strong conclusion, what you have to do is trying to derive the abundances of each of the specific molecules, atoms, that is consuming aluminium and aluminium oxides, and indeed seeing, can I really exclude aluminium oxides as potential grains here around Erdoradus? And so in order to understand this nice ALMA data, this very sensitive ALMA data, where we also have not only ground state, but also vibrationally excited aluminium oxide, we have to solve the non-LTE radiator transfer equations together then with the conservation of mass, energy, and momentum loss. And this is something that, for instance, Thijsa Danovic has been doing in various of her works. And you see here one of her model fits towards ALMA data. In black, you can see the ALMA data. In red, you can see here her predictions of this data. And this kind of predictions allow us to determine the abundances of these species. And so what do we see? Well, if we look towards all aluminium-bearing species that we have detected, we can see abundances around, let's say, few times 10 to the minus 7. But that's fine, since if we just would sum it up, all of that, this implies that less than 2% of all aluminium is occupied in all of that, in all of these molecules. But is that are these the only molecules? And now you have to build up your story. I have detected these molecules, but potentially, as I just have told you, there is a difference between being and seeing, maybe there are other molecules that I haven't detected yet. And so then you have to rely back on chemical predictions. One of these predictions has been done by David Hobrecht in 2016. We have used it also in 2017. And you can see here this aluminium oxides in black. You can see aluminium chlorides in the brownish color. And you can compare what these predictions give at the correct phase, or the pulsation phase, towards what we see here. And you can see that there is quite a nice correspondence. Sometimes we are still off with a factor of a few, but we are happy with that factor of a few. We see this aluminium OH, for instance, we see aluminium oxides, and we see also this aluminium chlorides. But what you should also see here is that there is the prediction that quite a lot of aluminium can be atomic. Is it atomic? We are not sure. The issue is that it is extremely difficult to observe atomic aluminium in these stars. There are some hints, but we can not at all constrain the atomic aluminium composition in these winds. So we are left over with that question mark. However, okay, that's a question mark, but let's continue our research. Okay, it might be atomic aluminium, but all of that aluminium in its most extreme can also be used to form aluminium-rich grains. Can that be the answer? Can all, if it's not in molecules, can all of the aluminium be in these grains? Since, you know, that star has, or at least we think it has, aluminium grains, aluminium-rich grains. You can see it here in purple, and it's the blackest Erdoradus. So you see here this alpha aluminium-203, so this is a corundum, the identification, and then you see this very broad shape, this is the amorphous Al203 in its spectrum composition. So let's do the exercise. Let's just take all of that remaining aluminium, put it into Al203 dust, and do the predictions. Well, then we had this surprise. This is the spectrum, and this is the prediction. Even in the most extreme model, where we put all of the remaining aluminium into the dust, we cannot predict the observed spectrum at all. We can, so what we have done in order to be able to predict that is adjusting the model, the wind model. And so what we propose in the paper with Theo Khoury is that you do not have, well, what you do have, at least what we think is you have the star, then you have a dust-free region in yellow, and then you have what we call a gravitational bound dust shell. It is a place where Al203 is present, but there is not yet a wind. So it's very calm and stable there. Under these conditions, we think aluminium-203 can grow toward two larger dust grains. And so still remember, larger dust grains can interact differently with the photons, and then potentially with some aid of the growth of some silicates on top of that, we then can have a dust wind over there. So you have, let's say, a two compositions or two regions in your vent, a bounded shell and then a shell which is free, so which could escape the gravitational potential. And then you can see indeed these blue predictions which are better in line with the model. But then came the reflection. If we say that this orange shell is Al203 and we do the computations of the temperature there, the temperatures are very high, around 1500 K. It implies that this cannot be amorphous Al203. It should be a glassy structure, so it should be crystalline in its formats. But if it is crystalline in its formats, it implies that we can predict potentially here this very little 11 micrometer feature here, but we cannot explain this very broad, so this brownish amorphous Al203, of which I was telling you, well, they think it is. So what if it's not amorphous Al203, what can then be the solution? What can be the origin? If it's not dust, well, maybe it's again gas. One of the things that we conjecture here is that the potential contribution towards this very broad species are very large aluminium clusters. So you can see here Al2O3 N with N larger than 34. Since laboratory experiments have shown that if you do this kind of experiments, that you then can have a spectral feature, as you can see it here in panel D, which is very much in resemblance with the amorphous corundum shape. So it's only a shape correspondence. We do not have any opacities from this kind of experiments, since they are in a kind of a nonlinear regime. So we cannot do proper computations and tell you, you know, it is compliant with the amount of with the amount of all aluminium, for instance, that I can have in this winds. So we're a little bit blocked here on that question.
46 minutes.
Why? Oh, okay. Can it then, if these are then the large clusters, then you might question then, if you have large clusters, can you also have small clusters? And then you can do the computations and you look at the fingerprints and you look if these fingerprints are present. And the answer is, well, if we look to all data we have, there is some resemblance, but the data is not yet good enough. So we will need METIS to answer that question if small clusters are present there. So the conundrum is still there. Are these the large grains? What can be the composition? Iron-free silicates or crystalline Al2O3. So I'll wrap up. Well, I will skip a few slides and it will go very rapid, since we have partly an answer to that question, and I will show you how it works. Well, give me this one. Anita, can I have a few more minutes?
I'm sure you can. It was merely a warning, not a cut-off. I'm sorry to interrupt.
No, it's fine. It's fine. So, conundrum, what is the state of the art? Let's first think back 20 years ago. Why was corundum, or why was it excluded? Well, people have been looking towards how stable is the unit, Al2O3 in its gaseous format. How stable is it? And just to tell you, the answer to that is Al2O3 in its gaseous format is very unstable. So that's why it has been included as being the first potential of a dust condensate. Although it can form from thermodynamic considerations, it can form at high temperatures. If you really look towards the chemical pathways, we have a problem, since the building block is just the gaseous building block is not there. And so if you then would indeed predict the nucleation rate from assuming gas phase chemical equilibrium, you should arrive here in this green box, but the predictions were only here the blue lines. So that was why it has been excluded. But then you say, if it is done in gas phase chemical equilibrium, maybe it is not chemical equilibrium, and it's true, you know, these things are just not happening in chemical equilibrium. We use that for the sake of simplicity of our calculations, but we should do proper chemical kinetics and understanding that. And so this is one of the predictions of Gilles Boulanger in 2019, where he has not assumed chemical equilibrium, and where he has on the full pulsational model. And first of all, he assumed these monomers to be present. And if the monomers are present, just look to my mouse, this is temperature, this is density. And you see that at these high temperatures, where we know and we have seen from observations that dust is forming, Al2O3 is there in high abundance. But you see my assumption, the monomer is present. So if I would get rid of that assumption and just start from an atomic composition, I am again back in the situation that Al2O3 is excluded, since I don't have the monomer in gaseous formats. And still, sometimes you should not always accept what you see. The reason for that is we still think it is the best candidates, since we know it is present in these pre-solar grains with much higher abundance than titanium oxide. We know we have observed it close to the star. We also know that, or we have quite good confidence in the molecules that we have detected with ALMA and in the chemical compositions that we can trace from this ALMA data. So potentially it's just our chemical knowledge which is not sufficient, and potentially we need to revise our way of thinking and the building blocks of being that monomer, Al2O3. And so what David Hobrecht has done recently is he has studied that. Can we bypass this very problematic monomer of Al2O3? And so just to guide you through the last slides, so if you just start with an atomic composition, you need to derive all kind of reaction rate coefficients to see which molecules and clusters can form. And this can be endothermic or exothermic. And exothermic means that it's much more easier, so you don't have this energy barrier, so it's much more easy to form. These are the ones in green, and it's difficult to form. Endothermic, it is in red. And you can see why Al2O3 is not easy to form, since the last pathway through it is indicated in red. So I cannot form it very easily. But maybe just do it differently. Instead of just get rid of the last one and maybe start from the one above, Al2O2. And look and extend, and this is what David and John Plain has done in a theoretical and a lab experiments. What can we understand if we start from Al2O3, and see if we can't form the last step. This is the dimer of Al2O3. And you can see that you can have pathways which are fully green, so quite easy, and which can give you Al2O3 in its dimer format. So what we need to do is not start from the monomer, just let the chemistry happen and see if we can have the building block from its dimer. And so if David is doing that, and if he's really using that building up of all the small molecules towards its larger gas phase species, you can see here his new predictions for this chemical kinetics. You have here Al2O3 n equals 4, which has quite a high abundance at the phase and at the region where we want it to have. So it seems that what ALMA has shown is in terms of there is a lot of aluminium still potentially free, that we have potentially now formed a gateway also of forming conundrum and of solving that, of forming corundum and of solving the conundrum of its formation. And so then you might wonder why I am so sticky towards that corundum. Well, we come back towards the start of the slides, these little meteorites. I have told you, we know their composition, we know where they are formed, and we know their birthplaces. Well, there are some grains which have clearly amorphous and crystalline Al2O3, and which either do not have titanium at all, or only a very small fraction of titanium, where if all of that weight percentage would be in one single grain, that should have been detected with the current instrumentation. So it is just thought that this titanium is across the grain, helps to stabilize the grain, and as such you can have a crystalline format. So I know it is there, and it can form also at high temperatures. And so this is why we still think that corundum is the first grains or the first dust grains that can form around these stars, or also potentially the first grains that will form once our sun will become a red giant stars and will potentially also engulf our own Earth. Since I say potentially engulf, since I want to know what are these first dust species, since that will determine the mass loss rate. And as you might know, the mass loss rate is in competition with tidal effects. And depending, and we are really just on that boundary, depending on the mass loss rate of the sun will be, the Earth will be engulfed by the sun or not. And so as such, the mass loss rate, the dust composition will determine the fate of our own planets once our sun will become an all-star. And with that, I would like to end this lecture. Thanks a lot.
Thank you very much, Leen. That was really amazing tour of, well, of how we all got here as being made of stardust.
Mm-hmm.
So I think that whilst Gergo is seeing whether, pardon me, whether there are any questions from the audience. One thing which I was wondering was when you were talking about the pathways for forming the aluminium oxide, the corundum clusters, and then also you were talking about the gravitationally bound dust shell. How long do you need for the wind from the star to be at a high enough density to form this, to form the corundum? What sort of time scale are you thinking of? Do we know that yet?
You mean in terms of chemistry or in terms of dynamics? Which time scale do you refer?
Oh, in terms, I was thinking in terms of the chemistry, given the assumed densities in that region.
So what you could, for instance, in this last slide of David, so this is really a pulsational model. And so that is a pulsation with a period of roughly a year. And you can see there that the building blocks already forming after a few months. So in the last part of the pulsation cycle. If it then comes into, will you have enough to form dust grains? Well, you need high densities. That's clear. Since these high densities, in general, nucleation is not a very efficient process. So you need these higher densities and let's say a quite quiet environment in order for that process to not be disrupted too often. So I haven't done the calculations now, but at least I think you need in the order of a decade or even more for these dust grains to grow large enough, but a decade is small for a star, but you need some time there before a wind can be launched.
Yeah, that sounds quite realistic from what we know of that area, and yeah, that's really interesting. We have a question from Abjit Borkar. Thank you for the excellent talk. I was wondering how common it is for the large multi-atomic, more than 2 to 3 atom molecules to form.
Yep. The larger the atom is, the difficult it is to form. That's a very easy answer, but it all depends on the bond energy. And as such, it is the bond energy, for instance, I'll first turn it around. The molecule which could be very favorable there, which has a high bond energy, is carbon monoxide. It is one of the molecules which has the highest abundance in that wind. But carbon monoxide is not very reactive towards other species. So understanding which ones do form is a combination of bond energy, dissociation energy, which is linked one to the other. It's a reactivity of the species. And so it's for that reason that you then can come up with the ones that I have shown you, the silicon oxide, the titanium oxide, but also this Al2O3. Al2O3 can be very, not in its monomer form, but otherwise it can be very stable. So it's a consideration of various aspects that gives you the prime candidates. But you should always have an open mind. It's not, since these are the prime candidates, that we are correct. We only can do what we do now, accounting for all knowledge that we have on the chemistry, but there's also a lot of knowledge that we do not know. If you now see these new predictions, this is since we have new chemical reaction rates, which are also often, or which can now sometimes be done at this high temperature. So this chemical reaction networks, it's a very big playground with a lot of unknowns. So whenever you have new lab or theoretical derivations, it can help you in constraining that answer. But it will never, in my opinion, be a very clear-cut answer.
Thank you. And we have a question now from Stefan Uttenthaler. And he says, I was wondering how large the micrometeorites are that can be found on rooftops and so on. Are they visible to the naked eye?
Yes, smaller than a nanometer. They are roughly 0.1 nanometer. And
Oh,
yeah. But there are some, apparently, you know, if I read a bit through these articles, which are quite interesting, people with a trained eye can see them roughly with their trained eye, with just from the morphology. And for sure, then you need to bring them to the lab to be sure that these are meteorites. But you can do that. So it's kind of a very nice way of getting some extraterrestrial knowledge.
wow.
Yeah.
And there is another question. Thinking towards the future, what is the next critical observation that is necessary or anticipated, and what instrumental capabilities are needed?
Okay, that's for clear. What we now have to do is, first of all, continuing this analysis of all this ALMA data that we have in hand, amongst which this atomium data, since they, Anita knows, this data are so extremely rich and they do contain so much information there that we barely has grasped now. Yeah. On top of that, we will, ALMA gives us a bit on the dust, what we can see there, but it's not a complete story. So we have to combine this ALMA data with also better diagnostics on the dust, on the dust grain sizes. And so as such, what we have been doing, for instance, for this atomium data, is we have at the same timing, we also have a sphere data. And so we are now in the process of combining the knowledge of the gas with that, what we can see in the sphere observations. And so this is, let's say, for the next 5 years, 4 years, 5 years, this is what we have to do. And we have, luckily, this great atomium team. We need to cross-correlate this ALMA data with this sphere data for these stars. And you can question me, why wouldn't you use James Webb for that? Well, we have stars which are too close by. They just saturate James Webb for that reason. Yeah, and we first need to understand, well, they are a gold mine and they will give us a lot of combined information on gas and dust species together.
Okay, well, I think that as we've used up our hour and a bit more, which was well worth it. I think that Leen's talk was definitely worth every minute. It was really interesting, and I think that the questions were from the rest of the audience were very sharp, which was reflected well on a talk as well. So thanks again to everybody here. The next European Art Network event will take place on December the 10th at 11 o'clock Central European time. But this will be an iTrain session on the use of a tool called StatCont, which is a statistically based method aimed at determining the continuum level in astronomical sources. And the next talk, the next ALMA Recounts of Cosmic Conundrums talk, will take place next year on January the 12th at 1400 Central European time. And this will be Eva Schinnerer from the Max Planck Institute for Astronomy, addressing the question, what is the coupling between molecular clouds, star formation, and stellar feedback? So if anybody has any questions about future events or would like to make use of the support offered by the ARC, of course, then don't hesitate to submit a help desk ticket or contact one of the ARC nodes directly. So thanks again to Leen, and thanks to ESO and particularly to Gergo Popping for organising this, and Anna Lopez-Sapulca for doing the behind the scenes work. And we look forward to seeing you all again soon. Thank you.
Thank you. Bye-bye.